The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. So today we start a new chapter, and it's the last chapter we're going to be covering this quarter. We're going to start with section 11.3, and we're going to be doing some more graphing. And so let's go ahead and get started. We have looked at linear equations. For example, y equals 2x, the graph of which would be a straight line. We've looked at quadratic or second degree equations, such as y equals x squared, the graph of which is a parabola. Today we're going to be looking at what are called exponential equations or exponential functions, which will be in the form of y equals something like 2 to the x, where the exponent is where the variable is. Before we get into graphing some more, I want to remind you of a couple of details. Let's say we have 3 to the -1 power, and we want to rewrite that with a positive exponent. That would be 1 over 3 to the 1 power, or 1/3. Let's say we had 3 to the -2 power. That would be 1 over 3 to the +2 power, or 1/9. Let's say we had 3 to the 0 power. What is anything other than 0 raised to the 0 power? It's
1.
Sorry. Any questions about that? Okay, well then we're going to go to the other program and do some graphing. Let's open this up. And let's see here. Let's see, we've got black ink there. Let's take a look at the graph of y equals 2 to the x power. As I've said in the past, when I'm graphing something that I, don't know anything about, I tend to start by graphing with x values going from -3 to +3. So let's take a look at what happens there. All right, so if x is -3, y equals 2 to the -3 power, which would be 1 over 2 to the +3 power, or 1 over 8, 1/8. We okay with that? All right. If x is -2, we have, okay, y equals 2 to the -2 power, which is 1 over 2 to the +2 power, or 1/4. If x is -1, y equals 2 to the -1 power, or 1 over 2 to the +1 power, or 1/2. If x equals 0, y equals 2 to the 0 power, which is 1. If x is 1, y equals 2 to the 1 power, which is 2. If x is 2, y equals 2 squared, which is 4. And if x is 3, y equals 2 cubed, which is 8. Now, when we graphed parabolas, there was a pattern where we had 2 different x values going to the same y value, so we ended up getting that parabola shape. Here, we don't have that same thing, but we do have somewhat of a pattern. Notice that these 2 numbers are reciprocals of one another, as are those, as are those. Okay, now let's graph this thing and see what it looks like. Okay. And put in some scale markings here. Okay. If x is -3, y is 1/8. So that's right about there. When x is -2, y is 1/4. So it moves up a little bit. At -1, we're finally up to 1/2. And then at x is 0, y is 1. X is 1, y is 2. X is 2, y is 4. X is 3, y is 8. So we get this situation. Now, that kind of looks like half a parabola, but suppose we continued on. If x was 4, y would be what? 2 to the 4th, which is 16, and then 32. And so this is going to just keep going up, okay? Again, that kind of looks like a parabola, but let's go the other direction. Let's say we used -4. That would be 1/16, and -5 would be 1/32. And so what's going to happen on the left end of this graph is that it's going to get closer and closer to 0. So it's not really going to look like a parabola at all. All right. Now, let's talk about some features of this equation. The domain would be all real numbers, because going to the left, we could take 2 to the -12 bazillion power. Okay, we get something very, very, very small. Let's take a look at the range. Well, the range, this thing never gets to 0, so it would be greater than 0. Okay. Also, we have no x-intercepts, because again, it doesn't cross the x-axis, and the y-intercept is at 0, 1. Okay, so can you see that the domain is all real numbers, the range is everything greater than 0, there's no x-intercepts, and the y-intercept is at 0, 1. Any questions about that information? All right, we're going to go back and graph another equation. Let's see here, we'll do this one in red. Y equals 3 to the x power. And let's see what we get here with our ordered pairs. So x and y, -3, -2, -1, 0, 1, 2, and 3. So now y equals 3 to the -3 power would be 1/3 cubed, which is 1/27. Okay. Y equals 3 to the -2 power would be 1/3 squared, which is 1/9. And then 1/3, and then 1, and 3, and 9, and 27. And I'm skipping the calculations there, but hopefully you could see that it'll produce those similar answers. So now, when x is -3, y is -1/27, and -1/9, 1/3. Here we're at 1, and then at 3, and then at 9, and then way up at 27, which is off the graph that I've provided here. Can you see that it's climbing steeper? Looks like I kind of missed this here. Okay, so if this is, let's see here. I can't show that very well. Well, can you see that y, for instance, y equals 4 to the x would be inside, and 5 to the x, and 6 to the x, etc. Okay, can you see how that would happen? Or do I need to convince you? No one's talking today. Everyone's fallen asleep.
It's raining out.
Yeah.
It makes sense.
Okay, let's go back and let's take a look at y equals 1/2 to the x. Okay, so now let's see here. Did it rain all night? or who knows? Nobody stayed up all night.
It was, I was up at 6 and it was raining then.
Yeah, how fun is that?
Yeah, it's been
Okay,
raining a while of it.
yeah. Let's take a look at this. Y equals 1/2 to the x power. So now 1/2 to the -3 power would be 2 over 1 to the 3rd power, which would be 2 to the 3rd power, which is 8. Okay. 1/2 to the -2 power would be 2 over 1 to the 2 power, which is 2 to the 2 power, which is 4. 1/2 to the -1 is 2 over 1 to the 1, which is 2 to the 1, which is 2. 1, a half, a fourth, an eighth. Okay, and again, I'm just trying to save some time in my calculations, but let's see what that thing would look like. X is -3, y is 8. X is -2, y is 4. X is -1, y is 2. X is 0, y is 1. 1 is a half, and a fourth, and an eighth. Can you see that that is a reflection of y equals 2 to the x? Okay, now, on all of these graphs, the domain is all real numbers. The range is greater than 0. There are no x-intercepts. The y-intercept is 1. Those are true of all of these. These first two, we say that they are increasing functions because both the black and the red graph get larger as they go from left to right. So it's increasing over its entire domain. This one, however, is decreasing over its entire domain. And so we get is this. If we have an equation in the form y equals b to the x, all right, if b is greater than 1, we have a graph that looks like that. If b is less than 1 but greater than 0, we have a graph that looks like that. Okay, now if b is negative, if you have something like this, let's see here. I'll go back, I'll do this in blue. Or no, let's do this in red. Let's say I've got y equals -2 to the x power. So the base is -2. Well, y equals -2 to the -3 is 1 over -2 cubed, which is -1/8. So at -3, we have -1/8. At -2, y equals -2 to the -2 power, which is 1 over -2 to the 2, which is 1/4. If x is -1, y equals -2 to the -1, which is 1 over -2, or -1/2. Well, what happens here? So when x is -3, y is -1/8. When x is -2, it goes up to 1/4. Then it goes down to 1/2. And this thing, I guess you could say, oscillates. And so, in fact, you can't graph it at all. So what we get is this base has to be greater than 0. Okay. If it's between 0 and 1, you get a decreasing function like the green one. If it's greater than 1, you get an increasing function like the original black one and the original red one. Okay. Any questions on that?
Why can't a graph oscillate?
Well, and maybe I shouldn't have even used that word. The problem is, okay, so if you had like a sound wave or something, it tends to do that, I think. But if I were to fill in the pieces in between, like, let's see, what do I want to say? Like, okay, look at this. Let's say that x was -2.5, okay? what happens then?
I guess then it would end up, the numbers would all end up.
Would all end up, yes, exactly. The best thing I could do, I'm not going to take the time right now, but on a graphing calculator, if you put it in there, it just sits there and spins. It won't work.
Okay, that makes sense. Thank you.
Okay. I mean, if you really wanted to explore it further, come back at my office hour and we can go and look into that, but it just doesn't work out.
Okay.
Likewise, if x, let's see, if the base is 1 to any power is just 1. So that's why it has to be, or I should have said this, I should have said the base can't equal 1. Okay, because when it does, you just get a straight line. So between 0 and 1, it decreases. Greater than 1, it increases. At x equals 1, or if the base equals 1, you get a straight line, which doesn't fit the pattern of an exponential function. So we've got this restriction on it, and then these conditions produce these kinds of graphs. Okay. Now, let's go to a new page. And I guess we're still with red. That's fine. Red works just fine. And let's go back and let's put in f of x equals 2 to the x, or y equals 2 to the x. And we'll find those, or plot those points again. And let's see here. This is what? 1/8, 1/4, 1/2, 1, 2, 4, and 8. And our graph, we have this, and then this, and then this, 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 and that. Okay, remember back in the previous chapter, if we graphed y equals x squared, we got this parabola. And then if we graphed y equals x squared plus 3, what happened to the parabola? Do you remember? Come on, it hasn't been that long. What did a plus 3 outside do? It moved the graph up 3 units. And if we had y equals x squared minus 2, it moved it down 2 units. You remember that? You're scaring me.
My internet keeps cutting out over here. I'm sorry about that. I missed most of it. I'm going to have to go back and watch the video.
Well, okay. Here's
Sinking rain.
Here's the point I want to make. If we have this equation, it's going to look exactly like the red one, but every point would be up 3 units. Okay, so now your domain is all real numbers. Your range is greater than 3. Your y-intercept is at 4. It's still increasing. Okay, what if you had this? Y equals 2 to the x minus 2. It's going to look just like the red equation, but everything's going to be down 2 units. So you'd have it here and here and here and here. Now your domain's all real numbers. Your range is greater than -2. Your y-intercept is at what? -1. And in this case, you have an x-intercept, don't you? So when you start messing with things and shifting them up and down, then it changes things like the range and the intercepts and whatnot. What about something like this? Y equals 2 to the x minus 1, where the minus 1 is part of the exponent. Well, that's going to shift the graph that way. 2 to the x plus 3, where the 3 is part of the exponent, would shift it that way, 3 units. Again, if you go back and look at what happened with the parabolas, the same thing happens with exponentials, except outside moves it up or down, and inside the exponent moves it left or right accordingly. Okay, that's all I want to say about that at this point. I want to look at some functions and talk about what they're going to look like. Let's go back here and open up this again. Let's see here. Okay. So let's say we've got something like this. A equals A equals 500 times 2/3 to the t power, where t is measured in years. Okay. Before I read all the details of the problem, let me ask you this. If t stands for time, at the beginning of the problem, when time is 0, how much of something is there? It says A equals 500 times 2/3 to the t power. So what is this thing going to look like? In fact, here, let's write it as a function. Let's say,
Mr. Mayo,
yes.
can't see your screen.
You can't see my screen. Well, that's not good. Thank you for telling me. How about now?
We can see it now.
Okay, thank you. Yes, I'm glad you didn't wait half an hour and it's like, could you? Okay, yeah, if you can't see what I'm doing, let me know. I may have forgotten to push the right or click the right thing. Okay, so we've got this function. A of t equals 500 times 2/3 to the t power. What would A of 0 equal? In other words, at the beginning of time for this problem. What's 2/3 to the 0 power?
Isn't it just 1?
It is. So what would A of 0 equal?
500?
So basically, this function, at the beginning of time, there are 500 of something. Okay? Do you see that?
Yes.
So this is like your starting value. Now, whatever this is, this 500 of something, as time goes on, is that 500 going to increase or decrease? Is this something that's growing or decaying?
Decaying.
How do you know that?
Well, I just kind of assumed because 500 times something less than 1.
Bingo. Less than 1. Go ahead. Sorry, keep going.
Oh, well, that's about it, to be honest.
Yeah. So the base is between 0 and 1, so it's going to decrease. Each time t increases by 1, you'll take the whole result and multiply it by 2/3. Well, something times 2/3 is going to be less than it was before. So if the base on the exponential part is between 0 and 1, this thing's going to decrease. Okay, now here's what it says. 500 grams of a radioactive material decays according to the formula which was given up there, where t is measured in years. Find the amount present in 10 years, round to the nearest 1/10 of a gram. So they want us to take A of t equals 500 times 2/3 to the t power and find A of 10, because t is time in years, and they want to know after 10 years. So now in our calculator, we've got 500 times the quantity, 2/3, raised to the 10th power. And it said round to the nearest 10th. And I'm getting 8.67, so that would be 8.7. And it said 500 grams, so 8.7 grams. So if at the beginning of time, there's 500 grams, after 10 years, there's 8.7 grams. You all right with that? Okay, well, I'll hope that that means yes.
Yes, it's good.
Okay, take a look at this function. P of t equals 6 million times 2.3 to the t. It says a colony of 6 million bacteria were determined to be growing in the culture medium shown in the illustration. And there's a drawing of some petri dishes, but you don't need to see those. Okay. If the population P of bacteria after T hours is given by this function, so T is time in hours, find the population in the culture later in the day using the information in the illustration. Okay. And what it does, it has 4 hours that go by. So we're going to find P of 4. But let me ask you this, and I guess I already read that. I shouldn't have read it first. Can you see that at the beginning of time, there would be 6 million? Because if this is 0, 2.3 to the 0 power is 1. 1 times 6 million is 6 million. Okay?
Okay.
Now, let me ask you this. Is this population going to grow or decay?
It's going to grow because its base is more than 1.
Exactly. Exactly. Good job. And let's see, does it say anything about rounding? I guess it rounds to the nearest bacteria. So 6 million times 2.3 to the 4th power is 167904600. So it goes from 6 million to 167 million in just 4 hours. Isn't that comforting to know? All right. Now, I want to look at another formula, and that is this. A equals P times the quantity 1 plus R divided by K, all to the KT power. This is the formula for compound interest, okay, where P is the principal. Let's see, R is the annual interest rate in decimal form. So in other words, not as a percent. We might be given it as a percent and then we have to convert it. K is the number of compoundings per year. So number of compoundings per year. T is the number of years, and A is the accumulated amount. I don't know if I spelled that right or not. There are 2 C's and accumulated. Oh, well, okay. So we've got all this information. All right. Now, let's see here. Let's take a look at a problem. It says compound interest. An initial deposit of $10,000 earns 8% interest, compounded quarterly. So every 3 months. How much will be in the account after 10 years? Okay, so A equals P times 1 plus R over K to the KT power. Okay, can never get my eraser to work correctly. Let's do this. Let's go P, R, K, T, and A. So an initial deposit of $10,000, that's our principal, earns 8% interest. That's the annual rate, which converted into a decimal, 8%, 0.08. Compounded quarterly, so 4 times per year. How much will be in the account after 10 years? So our question is the accumulated amount. All right. Any questions yet? So A equals 10,000 times parentheses 1 plus 0.08 divided by 4, all raised to the 4 times 10 power. Now, there are a couple of ways you can do the calculation. You can leave everything as it is and punch it all into the calculator. Or if there are some things that can be simplified first, as long as you don't approximate, as long as they come out exact, you can do that. For instance, 4 times 10 is 40. 0.08 times or divided by 4 is 0.02. So you could simplify this if you wanted to down to, let's see, that, and then you could simplify it even further, and you could put that into the calculator. Okay, but if something like this doesn't come out exact, then you've got to leave it in its original form, because you don't want to round off until the very end, if at all. Okay, so we've got 10,000 times 1.02 to the 40th power, and I get 22,080.39664. Now, we're talking money, so even though it doesn't say anything about rounding, we would round to the nearest cent, which is right there, right? Because this is dollars, this is your 10 cents, your 1 cent. The 6 would round up. So you'd have 2, let's see, actually that zero's in the wrong place, isn't it? My bad, it should be there. You'd have 22,080.40. So $22,080.40. So if you deposit $10,000 at 8% compounded quarterly for 10 years, you'll more than double your money, won't you? But nowadays you don't get 8%. You're lucky to get 0.8% at a savings institution. All right, any questions about this problem? Okay. Let's take a look at another example. How are we doing for time? We've got time. This says an initial deposit of $10,000 earns 8% interest. This seems awfully familiar. Compounded monthly. Oh, so now K is 12. And let's see here. How much will there be after 10 years? So everything's the same except the number of compoundings, okay? Instead of being compounded 4 times, it'll be compounded 12 times. And how does that work? Let's go back and let's talk about this quarterly first. So let's say you get interest that's compounded annually. At the end of the year, they put some interest in your account, and then it sits there along with the principal for another year. And then at the end of the year, they put some interest in your account, okay? If it's compounded quarterly, that means after 3 months, you get 3 months worth of interest, which would be not 8%. It'd be what, 1/4 of that, so 2%. But the point is, you get a little bit of interest put in the account after 3 months. Well, then for the next 3 months, you're getting interest on the original principal, plus you're getting interest on that interest. And then the next 3 months, you're getting interest on the original principal, interest on the interest, and interest on the interest on the interest, blah, 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 blah. And that's that whole idea of compounding. But everything else remaining the same, If we compound it 4 times a year, we get this. Let's see what happens if we compound it 12 times a year, if it changes things. And if so, how much? Let's see, this is, okay. Now, if I take 0.08 divided by, whoops, got to turn your calculator on first, 0.08 divided by 12, it comes out 0.006 repeating. So I can't really simplify that part of the problem. I can, however, take 12 times 10 and get 120. So now in my calculator, I'm going to put in 10,000 parentheses 1 plus 0.08 divided by 12, and then I'm going to close up the parentheses and then raise that to the 120th power. When I do that, I get 22196.402, which would be $22,196.40. Okay, so let's compare that. This was 2280.40, so 2280.40. So by compounding it 12 times a year instead of 4 times a year, we got what, $116 more? Everything else was the same. So the number of times it's compounded per year affects the final outcome. Important to know. Okay. Let's see here.
Could you real quick go back to the previous slide
Like that?
and compare it? Yes.
I can. I can even do it really slowly if you'd like.
And if you were to go to slide 11, I was just wanting to compare those for a moment.
That's slide 11 there.
All right,
So-
thank you.
So this was the new amount. This was this 12 times, and this was the 4 times. Compounded 12 times versus 4 times. Okay. All right. How about this? If $1 had been invested on July 4th, 1776, at 5% interest, compounded annually, and let me talk about that for a minute, okay? Compounded annually means 1 time a year. Semi-annually is twice a year. Quarterly is 4 times a year. Monthly would be 12 times a year. Daily would be 365 times a year, et cetera, okay? All right, this is compounded annually. So the principal is $1. The interest rate is 5% or 0.05. The number of compoundings per year is 1. It says, how much would it be worth on July 4th, 2076? So we started in 1776 and we went to 2076. So how many years have gone by in that problem? What is the time and the number of years?
300.
Good, 300. So A equals 1 times 1 plus 0.05 over 1 to the 1 times 300 years. A equals 1 times 1.05 to the 300. A basically taking it times 1, we're just going to get the same thing, right? So if we take 1.05 to the 300th power, we get 2273996.129, which would round up to 2273996.13. So that $1 invested would be worth $2,273,996.13. Every once in a while, you hear a story about somebody that was going through an old attic trunk or something, and they found like some stocks from the 1800s, and and oh, are they still good, and are they worth millions of dollars? And yeah, you always wonder, were they still? I can't imagine what you could invest $1 in back then that the company would still be in business, but you never know. You never know. Okay. Well, that's all I've got for you today. So I'm going to stop the recording.